Hey guys, Mr. Betts here. I want to take a look at another convergence test, and this one's pretty similar to the direct comparison test, but it's also going to be a little bit more valuable because if you remember with a direct comparison test, we were not able to make a conclusion about this particular series. So if you remember, we were comparing to the harmonic series, and since I'm going to make the harmonic series n over n squared for our comparison, since the numerator is smaller in our test series, then that means that term by term, this series is smaller than a series we know diverges. Well, depending on how much smaller, this series may also diverge or it may converge. We don't know. However, I did mention that this still does behave like the harmonic series. So as n gets really, really big, the terms are going to be approaching 1 over n, which is the harmonic series. So rather than directly comparing them term by term, what we're going to do is we're going to show that this behaves like the comparison series of the harmonic series. And we're going to look at the limit as n approaches infinity of the test series divided by the comparison series. And this is going to be the same thing as the limit as n approaches infinity of n minus 1 over n squared times n over 1. And the degree on top and bottom are the same. The leading coefficients are the same, and this limit is 1. So what this limit is telling me right here is very similar to what the ratio test limit told us with a series behaving like a geometric series. So essentially, this is telling us that this series behaves like the harmonic series as n gets really big. So if you imagine we plug in, say, a billion minus 1 over a billion squared is really, really, really close to 1 over a billion. And as n gets even bigger, they get even closer to the corresponding terms in the harmonic series. Since the harmonic series diverges, this behaves like the harmonic series, this series will also diverge. Now, I want to change this up just a little bit to talk about how we can handle something like this. So if this is 2n minus 1 here, this ratio is going to be 2. Well, what that tells us is that our test series is behaving like double the harmonic series. And so since the harmonic series has an infinite sum, if we were to double that, then this series would also have an infinite sum. So this limit here doesn't have to be 1. It doesn't have to say it behaves exactly like it, but it's behaving like double the harmonic series. And like I said, double infinity is still infinity. If I change it up again and make the 2 in the bottom, now what this is saying is that our test series is behaving like half of the harmonic series. Well, the harmonic series is still adding up to infinity, still has an infinite sum, and half of an infinite sum is still infinite. So obviously it's going to take a little bit longer to grow as big, but it is going to grow without bounds still. So the fact that this is any constant, so anything that's not zero, anything that's not infinity, tells us that they're behaving either the same or a constant multiple of each other, and a constant multiple times infinity is still infinity. Likewise, if this were a convergent series, or if we were comparing to a convergent series, that means that that series has a finite sum. So regardless of what this constant is, if it is a constant that's not zero, nor is it infinite, then the sum is going to approach a constant multiple of a finite sum, which is itself going to be finite. So that gives us the limit comparison test. This is a little bit simpler because when we use the limit comparison test, we don't have a whole bunch of cases. We really only have 2 cases. If we choose our comparison series wisely and we get a limit when we compare the test series to the comparison series using a ratio, if we get a limit that is a finite number between 0 and infinity, so I do want to say this formally doesn't actually mean anything. It's just saying that L is finite, and it's greater than 0, then both series have to either converge or diverge. Okay, so if we choose a comparison series wisely, that this limit is some finite number, then we're going to know that they're both going to do the same thing. So then if we know the comparison series diverges, then we know the test series diverges. If we know the comparison series converges, then we know the test series converges. So a few notes about this. One, it doesn't really matter which one's on the top or bottom. I will always put the test series on top and the comparison series on the bottom. But if you were to flip it, that's like saying that, well, we get either 2 or 1/2, depending on which way we write it. So we're going to get a constant one way or the other. It's just going to be the reciprocal. The important thing is what that constant that we get has to be non-zero and finite. Also, we get to choose the comparison series. We're not going to be told what it is. So we get to choose that a comparison series that makes things easy for us. One, we're going to choose comparison series that are easy to determine if they converge or diverge. We'll often use the p-series test, but we'll also sometimes use geometric series. Although if a geometric series would work, then the ratio test would also work in that case. But as you could probably guess, several of these tests, these conversion tests, might work on any one series. Also, we want to choose our comparison series that we get a limit that falls in that finite non-zero range. I also want to go back and point out here that we're talking about absolute series, which means that we're talking about absolute convergence. So if we have a series that is an alternating series, we will still use this as an absolute convergence test, which means that we're going to be looking at absolute values on really the test series, and then the comparison series, we will just choose an absolute series. If that's the case and it still converges, then it's going to converge absolutely. If it's an alternating series and it diverges, then using the alternating series test, it may converge or diverge, and if it converges, then it would converge conditionally. I also want to mention that there are special cases that we shouldn't really ever need if we choose our comparison series wisely. However, these special cases are more similar to the direct comparison test because if we get a limit where essentially the test series is so much bigger than the comparison series that the limit goes to infinity, then if the comparison series, if the bottom diverges and the top is bigger, then the test series will also have to diverge. Okay. On the other hand, if the limit is 0 and this series converges, to make the limit 0, the test series is going to have to be smaller and would therefore also converge. I wouldn't worry about memorizing these special cases because if we use the standard case and choose our comparison series wisely, then we won't have to use these special cases.